We'll introduce some important circuits today. So let's look at the get a quick review on ISR latch really quick. Which is, if this is Q, this is Q naught, which is R, which is S. Okay, if I have a switch connect to the ground and I pull this up to 5 volts, usually 10K resistor as a pull-up resistor. That could be an interview question if you don't know what is a pull-up resistor. Usually 10K, 1K is too small, drawing a lot of current. So you usually use 10K. Why is it called pull-up resistor? No. They pull the voltage up to 5. But it's not why it's pulling up. Why is that? It's not pulling, obviously. Why is we call it? It's a pulling. Not sure? Because when you don't have a circuit, you have a disconnect circuit over here, right? So it's not a complete circuit. Then there's no current running through this node from the power source. So no, just 5 volts. So no current, no voltage drop. From here to here, there's no drop. So it's basically 5 volts over here. It's being put up. Okay, but if you connect this to ground, definitely this is not putting this node up to 5 volts at all. Okay? If I connect this to ground, for example, the voltage here will be dropped to 0 because it's shorted to 0. Okay. If I have another put up to 5 volts, sorry. Okay. That's nodes. And initially the switch connect to the first, the top one, and then at the moment I'm going to switch it to the bottom. Okay, if I just use a very simple switch, for instance, it initially was here and now I switched it to here in order to connect it to a node which has a load resistor and also has a VL. It's just RL, it's a load resistor or any kind of load in the circuit. This is the switch. I started moving this one here. I mean, for you, it's a really fast switch, but actually to electronics, which is running at 60 megahertz, it's super slow. It travels a long distance from here to here, which causes a lot of bounces back and forth from 5 volts to ground. Because the mechanical connection is not that solid. It's not making a solid connection every time. It's bouncing back and forth because of the mechanical property of the material, right? So which will cause the voltage, for example, at the very beginning, it was, before I switch it to here, what's the voltage at V out? Before I switch it here, what's the voltage here? And this resistor is called? It's a pull down resistor, right? So it was 0, right? Okay. If I switch it here, wait, is that changing anything? No, it's not. So I probably have to pull it up. Okay. No. So if I don't turn on this, it becomes a push button. So it looks weird. But it works, okay? So if I don't connect this one to ground, this is put up to 5 volts, right? It was 5 volts. right? And if I try to switch it on or close the switch, it's shorting this pin to ground, but it's bouncing back and forth in between the switch and the contact over here. So it won't be a solid 5 because it's on and off. Whenever this is off, it becomes 5. Whenever it's on, it's shorting this to ground. So it's actually bouncing back and forth for a while and then eventually being put down to ground. Is ground the final voltage after it becomes stable? Is that going to be 0 volts or 5 volts whenever it's stable after the switch is being turned on? 0 volts because it's shorted, right? Here's more difficult because it has a resistor on the top. It's going to be a 0 volts. Okay, so to avoid that, we can add a debounce circuit over here using an SR latch. And now let's see how that works and why it works, okay? So you can see the R and S are both put up to 5 volts. So if I don't have a switch here, they are both 1s. Remember for the NAND gate SR latch, if you have both 1s, what is the circuit doing? What's the latch doing here? The memory or unused or set or reset? It's a memory because 1 is not changing anything to the NAND gate. Okay, so it's a memory. Okay, and if I have a switch at the very beginning, the switch is making a contact or connection to the top node, which is R. Okay, what is the output for Q? If I don't touch it, it's making a solid connection to the top and it's shorting R to ground, right? So you're having 1, 0. Okay, if S the set pin is 1 and R is 0, you are setting or resetting Q. Setting, okay, so Q is 1. Q is 1 at the very beginning, right? And when you start moving the switch to here, although it's really fast to you, but actually it's traveling. When it travels, okay, it was in the middle, okay, at the very beginning. So when it's in the middle, what's going to happen? It's a memory, so it's not changing Q, which is good, okay. So what if there's a there's a vibration here? So when I move it away from R, there might be a little vibration there as well. For example, it's giving R a 011001110 for a while. What's going to happen? Doesn't matter why. Yes. Okay. That's why we want to use this SR latch because it holds it at the memory state. Let's see. You may need to put it down. See if that works. But let's finish this one first. Okay. So when the switch travels, it's a memory, and when it reaches S, there will be a vibration as well, right? But R definitely because when it's getting closer to S, it's away from R, so R will be a solid 1. But S will be bouncing back and forth. Okay, what's going to happen? So if this one is 0, 1, 0, 1, 0, 1, but this becomes a solid 1 because it's already moving away from R, right? So R will be 1. So it's going to reset it. Okay, but are we getting a noisy edge or a clean edge? Clean or noisy? Yeah, yeah. Even though this is bouncing back and forth over here, there's a vibration, but R will be asserted. So in digital, when we say it's being asserted, which means it's active. Okay, it's moving away from R, so R will be immediately put up to 5 volts. So R becomes a solid 1. Okay, so we'll reset Q. So it's going to give you a solid 0 instead of bouncing back and forth. When it travels in the middle, it doesn't matter because it's going to be a memory or 0, right? 1, 1 or 1, 0 doesn't matter. So it's going to be a solid 0 for Q. So that's how it debounces your switch. So if we have a NOR gate, So the question is, should we pull it down to ground or not? We should, right? Because when the switch travels, we want one of the pins to be asserted and give them a 0. Will be a memory state. So we need a 1 here. Would that work? So if we keep this switch contact R here, then we are having a 1, 0, right? Because this one is being put down to ground. So S is being put down to ground. This is 1, 0, okay? So when this travels in the middle, you got a 0, 0 as a memory. It's not changing Q. And when it reaches S, it bounces back and forth, but this one will give a 0. It doesn't work. Because 0 is not turning on R. It's either memory or a 1. Yeah, it works. It works because if this one vibrate, right, it's gonna reach a 1. It's gonna reach a 1 at a moment. So whenever it reaches 1, it's gonna set this point. And even though it comes back to 0, it's just a memory. It's not changing Q. Still gonna work. Okay. I think so, yeah. Mm. I was thinking if we can debounce the push button, but I didn't find a solution. The switch is different. Switch, you have like 3 nodes, right? Or you are making a connection between these 2 nodes. So it's either shorting this one or shorting this one. But if you are using a push button, it usually, so push button in your Arduino box, it looks like there's a button here and you have 4 connections, 4 pins, and the top 2 are shorted and the bottom 2 are shorted together internally. Okay, so you can make the connection here, here. So if you push it, you make the connection here. Okay, that's how that works. So if you draw the symbol, it looks like this. You put it up and you ground it here, 10K, 5 volts. And usually you have the connection from the top, because at the very beginning it's being put up. If you don't push it, it's a disconnect circuit. So this pin is being put up to 5 volts, right? If you push it, it makes a connection. It's being shorted to ground. So there's a serious bouncing problem. You would need to debounce the push button as well. But usually we do it in software, right? Arduino code using the time delay. But can we use a latch to debounce it? I was drawing on the paper, but didn't find a solution. You can let me know how it works. Just that'll be great next time. Okay. Did you see the difference? So if we just do a similar way like this, right? For example, if we have a push button, here's a button, right? And I connect these 2 pins, one to R1 to S. This is Q. This is R, this is S. Can I debounce it? So if I don't push it, the result is, because R is being put up to 5, right? So R is 1, S is 0, right? Being R is shorted to ground. So Q is 0 at the very beginning. That's right. Yeah, if you push it, it's a memory. How to debounce the push button? There must be a way to do it in hardware. Probably can figure that out on Wednesday. I don't know. And you can also do a search on it if you want. Let's talk about flip-flops, D flip-flops. So last time we introduced D flip-flop to you guys, which is you have SR latch, and you got a clock stage, add a clock here, add an inverter here, so this becomes D. And this is Q, right? It's a data flip-flop, which means when clock is active, you are sending D to Q. That's a data, right? Data. It's not a inverse the data. It's just a data to Q, D to Q if the clock is active. And this is called a level triggered D flip-flop. Because whenever a clock is active, you cannot control it. When D changes, Q changes. It has a lot of problems with that. Okay, so we are trying to develop some edge triggered D flip-flop instead of level triggered. So it only happens at the edge because if you look at the clock signal, the level takes a lot of time over here. It's a longer time compared to the edge. So the edge happens really quickly. Very unlikely the signal will change during the edge, but very likely it's going to change during the on time or off time. So we just want to trigger that data transmission during the edge. So when D changes, our output is not changing, not following. Okay, that's a goal. So how to design a edge triggered D flip-flop? We can still use the basic structure of the SR flip-flop, but adding one more stage of it and just following that. So for example, we have one, that's the first stage of it. And just add it to another stage. Still do the same thing to the input, so this becomes D. It's feeding the signal back to the input. And this is clock, and we invert it to make a clock for the second stage. Let's see how that works. So don't worry about the feedback for now, okay? Just look at the two stages. If clock is, for example, we have a rising edge coming, what's gonna happen? Don't worry about this, just ignore this feedback for now, okay? When at the rising edge, because this is just basically just a D flip-flop, we just drew on the paper in the last page, okay? And this D will be sent to here, and there's no control, so D, this becomes D bar, and this will be D, because this is Q for the first stage, right? So this is D. However, when the first clock here for the front stage is on, or right after the rising edge becomes on, this is getting inverted, right? So this is actually a falling edge. What's happening for this stage? So it deactivates the second stage. So data will be stored over here. You have some parasitic capacitors will hold the charge. So whatever D is, can be 1, can be 0, is going to be held over here after the rising edge. Okay, so when the rising edge, so after a while, then the clock will have a falling edge later on. So for this clock, okay, so if you have a falling edge for this clock, it's going to be a rising edge for this clock. It's being inverted. Okay, so the rising edge will send D to Q for the second stage. So this is called asynchronous flip-flop. And I'll let you guys tell me if it's rising edge triggered or falling edge triggered. Or maybe we can say this is confusing. It's at the rising edge, it samples the data, and the falling edge it sends the data to Q. So it's not doing that at the same time. So it's like rising edge, we lock the second stage, it's not going through to Q. The rising edge, I sample it. I sample the data here because these are just passive logic gates, combinational logic. So you cannot control it. Whenever you activate the clock, it activates all the gates here. So it's going to be sent to here. So it's going to pass through this one freely to here at the rising edge. We are saying this is level triggered. So whenever clock is on, D will keep going to here. Is that correct? Are you blocking D to reach this point whenever clock is on? Just want you guys to have an intuitive understanding of what's happening for this circuit. Let's just look at the first stage. All right? And ignore the feedback. The feedback is not affecting anything, okay? It's always one. So if the clock, this is the clock directly connect to the clock for the first stage, okay? If the clock have the rising edge, okay? So rising edge, we are considering the rising edge as 1 because the rising edge, these two gates will be activated and D will pass through this gate and this gate and arrives here. Okay? So after the rising edge, the clock will be on for a while. So when the clock is on, if D changes, would this change or not? Yeah, but it's going to change. Okay, so it allows this one to change, which is not ideal. It changes, right? Okay, so at the falling edge, actually the falling edge samples everything. A falling edge samples and then triggers Q at the same time. You know what I mean? We're assuming D is not changing. For example, D is here, okay? So we're assuming D is way slower than our clock. So your clock is like this, all right? And to here, you got a clock like this. Okay, so rising edge, what's gonna happen? Or during this period, including this period, D will arrive here, right? Okay, but won't affect the Q, okay? But only when you got a falling edge, clock is falling edge and being inverted to the second stage, it becomes a rising edge. Okay, so at this time, D will arrive Q, and the first stage will be blocked, will be off or deactivated because the clock becomes 0 after holding edge. So if D changes during this period, it's not going to affect the Q anymore. It's basically the folding edge triggers Q, right? The rising edge does sample D to here, but it's still changing, so it's not actually helping anything. It just arrives here. But the folding edge will trigger the transmission from D to Q. Okay? So the folding edge triggered. But we're not using this one because you can see this type of flip-flop everywhere. But basically you cannot not really use it for design. The reason is you cannot set and reset it. I was trying to design a set and reset circuit to this D flip-flop. This never works because I want a Q and Q naught to be Q and Q naught instead of the same data. Okay, so I was trying to add, for example, how do you set and reset this circuit? Okay, how could you do that? If I have, for example, set, okay, a pin of set, for example, this is the chip, right? And there's a pin for S, and I'm shorting S to a inverter and I feed the inverter here. All right, if S is 1, what's going to happen? I'm trying to set Q, right? If S is 1, this becomes 0, right? And 0 will give you a 1 for Q. You're saying, hey, I'm setting Q, great. And now I got a 1 here, 1 here, but you don't really know what is the signal over here. Okay, if you have a 0 here at the same time, then you got 2 1s. All right, same for reset. If you have a reset pin connect to the NAND gate over here, trying to you have to invert it as well, right? If R is 1, you got a 0 here, you got a 1, but this can be 1 at the same time, and you are not actually resetting Q. You are trying to give a 1 to Q naught. You are assuming Q will become 0, but actually you couldn't control that. Anyway, so this is not practical at all. Okay, you can see this a lot of textbooks, but they will just not let you know that this is not practical. You cannot use it for anything. So because a lot of times when you use a D flip-flop in the digital circuit, you need to set and reset the circuit. So I was able to find a few, 2 different designs. And this is the IC circuit or schematic from a TI's D flip-flop. It's off the shelf D flip-flop. That's a schematic of it. Okay.
For the last example,
yeah.
Where it's the falling edge triggered,
mm-hmm.
Do you think that also is that's when the memory is stored? So that's why it's triggered at that point. Once we decided here's where our memory
mm-hmm.
would be, and that's where the falling edge
is. It's just the 2 NAND gates here are memory. It's not memorizing it because the 2 pins are always inverted. So it's not entering a memory state, right? But Q could be, but you are right. So whenever whenever the clock is 1, right? When clock is 1, is activated. So 1 0 will be flipped, become a 0 1 here. But when this one got triggered, this one becomes a memory. That's right. Only when this clock is active. Because when this is active, which means you got a 1 here, rising edge and a 1 for this clock, right? So which means because it's inverted, so this one must be falling edge or 0. So having a 2 1s here. So 2 1s will give you a memory for this point. So it's not changing. It keeps at D. And then this one get activated, so D will be just passed through the 2 gates, the revs Q. Okay. All right, for this D flip-flop, didn't expect that. It's just so big. Let's see if I can change it. Okay, that's everything of the circuit. I want to verify that this is a D flip-flop instead of something else. But it doesn't have a set and reset for now, but we're going to add set and reset to it later. But you're very familiar with this structure, right? Okay, this is a SR latch and a lot of other connections over here. So let's verify it's a D flip-flop, which means at the edge of the clock, it passes D to Q instead of D bar or something else. Okay, it passes D, which is data here, to Q. Let's assuming it was 0, but there will be a rising edge later. Okay, so when clock 0, what's going to happen to the circuit? What can we know? When it is 0 here, you got 2 zeros to the 2 NAND gates, right? What's going to happen? You got, see? Yeah, ones, yeah, 1, 1, right? So when clock 0, you got 2 ones. It's keeping the latch at the memory state, which is good, right? So because previously it must be at something else. And when clock is 0, I don't want to do anything. Just keep it as what it is. All right. However, at the rising edge, where consider rising edge is a very fast 1. So it's giving a 1 really quickly, changing clocks from 0 to 1. And then we'll keep at 1 for a while. Okay. So this is D, right? Okay. It was 1 when clock is low. It was 1, no problem. So what is the output here? Or what was output here when clock is 0? One and a D naught, right? Okay, so we got D naught, because that's the same line. Okay, 1 here, D, D. Okay, is that stable? That's when clock's 0. Is that stable? Is it changing or oscillating? Because the gates have delays, right? If after the signal travels through the gates and then it's inverting these signals, which means it's not stable, it's going to oscillate because of the time delay. Okay, for example, like what we just did, right? When we use a signal and it travels through the gates, when we find out, wait, I got a D, then this will be flipped to 0. Then it's going to oscillate. Then it will come back here and then whatever to whatever. But this is not the case here. Is it stable? We're talking about when clock is 0, you got a 0 here, right? It's always 1. So it is stable. Then at the rising edge, or we're considering the rising edge is a really fast 1, what's going to happen? So these stars changes from 0 to 1, right? Changes from 0 to 1. anything else will change. This this was 1, right? Because the clock changes first. That's something changes from the circuit. So this changes first. And this was still at 1 because it's holding the charge at 1, right? So this was a 1. And 1 comes over here, you got a 1, 1, D naught. So this becomes 1, 1, D naught. 1, 1 is still 1, right? And 1 and the D naught is still D naught. And D naught getting inverted. So this will change from 1 to D at the rising edge. Okay? Same to here. All right, is this stable? Is this stable? Yes, still D naught. Still D naught. Still D naught. What else is going to change? You got a 1 here instead of 0, right? Stable, D. D and 1 will be D, and this becomes, okay. That's a instantaneous change. It's going to happen after the rising edge. And now let's see if this is stable. D naught. So this becomes D naught, right? Or 1 to D naught. So D naught, 1, D, no problem, right? D naught and D naught and 1, still D naught, inverted D. Okay, D, 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 D naught, no problem, stable. D naught, D naught, D naught, 1, D, no problem. D, D, 1, D naught. Perfect, stable, all right? So I'm gonna stay at these two states. And now let's see if Q is gonna be D. How do we verify that? Yeah, so this is R, this is S, right? No, this is S. If you have D naught and D, I mean, for example, if D is 1, right? If D is wait, so let's see D and Q, okay? If D is 1, this becomes 0, and this is 1, right? So Q will be 1. If D is 0, this is 1, this is 0, and we're resetting it, so Q is 0. So Q is D, D is Q, no problem. And DQ is ice cream. All right. Is that D flip-flop? Yes, because it's passing D to Q. Now we want to verify if this guy is changing during this period, during the rising edge, if it's changing. How do we verify that? Why do we want to verify if it's changing at during here? Why do we want to do that? Because we want to have a edge triggered, and this very likely this will be a rising edge triggered. So we want, because we know at the rising edge it changes, right? It sends D2Q and samples D2Q. And now I want to verify if D changes during the voltage high over here and Q is not being changed, then we can get a conclusion that first, this is D flip-flop, and second, it's a rising edge triggered because at when the clock is high and when D changes, it's not passing the change to Q. It keeps at D. So it only samples the data at the rising edge. but not sampling or changing Q during the voltage high or during the logic 1 period. So how do we verify that? I was thinking we probably can do this, right? So the first time I use a single line arrow here to show you the change from 0 to 1 of the clock, which is the rising edge change. It's gonna make the change from left to right. I'm using a single line arrow. But now I'm doing a double line arrow here to show you that when D changes to D bar, it's binary, only can happen in this D bar, cannot be something else, right? So if it changes, it's going to be D bar. If this changes to D bar, as a next step change, I'm going to always use double line arrow, and eventually we can see if Q is being changed or not. So if D changes to D bar, what's going to happen to here? Because we know right now the states are stable, all the D's and whatever, they're stable right now, right? So if D changes to D bar, what's going to happen to this one? It was a D here, right? So D bar and will be 0, and NAND will be 1, right? This becomes 1. So this becomes 1. Okay. What else? Same line here. So this becomes 1. This becomes 0. Is that correct? Is there anything here will be changed or not? On my notes, this changes. Oh, we haven't done this yet. Oh, it was 1, right? We should copy the same line, right? It's already D naught right now. That's from the last date. So it became D naught already, but we didn't update it. There's another one we should update actually. Oh, we did it here. Good. Okay. So this now is D naught, right? And this becomes 1. So 1 and a D naught will be D. So this is still D, right? So this is still D. Because this is being kept at 1 at the logic 1, right? So this is 1 still 1, no problem. 1 and the D will be D, and D naught will be D naught, right? So it's not changing here. What about here? Because this is not changing, so this is still D naught, right? Yeah, D naught, 1, 1, still D. So if D changes, it's not sending the change to Q. It's holding at D. So now the conclusion is this guy is a D flip-flop, it's passing D to Q, and this guy is a rising edge triggered. Now let's add in set and reset to it. I have a hard time to show all the circuit. Like this. So what are the changes we have to the circuit? So because we have a set and reset, so I think we should verify set and reset first. For example, let's do reset first. See if that works. If you see a bar on the signal line, which means it's a zero active, whenever you give a zero, you activate it, right? If I see a bar on the top. So if you want to reset it, what are the signals we need to give to these two lines? Yeah. Wait, 0 and 1, right? Okay, we don't want to activate this one. We're resetting only, not setting. Yeah, so it's a zero active, has a bar on top. It's zero active. That's why we need to give a 0 to reset. And now let's see if I'm resetting Q. Because this is a functioning D flip-flop, so when Q is 1 or Q0, Q naught has to be 1, right? So set is 1, this is 1, this is 1. Not doing anything. Reset is 0, we get a 0, 0, 1, 1, 1, 1. 0 is the same line here, got a 0 here. 1. Anything else? We care about the clock. Clock shouldn't matter, right? If I'm resetting it, doesn't matter what the clock is, I should be able to reset Q. What's happening? You got a 1, 1, 1. What's happening here? Right? Are you resetting it? Are you resetting it? Done, right? 0, 1, done. I'm resetting Q. It's already reset being reset. And Q naught is 1, perfect. It's perfect. Okay. What about set? Can we set it? So set, you need a what voltage to reset? Right? 0, boom, 1. 0, 1, no problem. 1, same thing, 1. Right? Now for here, 1, 1, 1, 1, 1, it's the same signal. Can we draw a conclusion here? For set. Do we need more info? Yeah. So this is clock. Let's just name it as clock, right? This is clock. Okay. So the 1 clock 1, so this becomes clock bar, right? Clock bar, clock. Can determine what the result will be. Clock bar and the clock will be definitely 0, right? You're getting a 0 for the NAND gate, so this is definitely 1, right? Okay. 1, 1, 1, 0, 0. Clock bar, so 0, clock bar 0, 1. Okay. Are you setting it? Are we setting or resetting it right now? Yeah, because it's a 0 active, right? So we are trying to set it, and now it's getting set. All right. So set and reset works. And now I want to see if it's rising and shader defect file. I don't think we still have time to do it. Yeah, so 2 minutes left. So let's do it on Wednesday. And so tomorrow will be the second part of the lab, I think, right? So guys will just keep working on that. So for these defect file analysis, I want you guys to be able to do it as what I just did over here. So eventually there will be a quiz. I'm going to give you some copies of the schematics and let you write onto the schematic and maybe sit here and show all the process to all of us. That's what we did last year actually. So we used, but we didn't do it with these schematics. These are easier. So we did it with these ones. This is another defect file schematic. I think was pretty fun. Max and Seth and Mason they were just over here and writing on the board and going through all the signal from through all the planes. Yeah, that'd be help. Okay. All right, we'll see you guys tomorrow in the lab.